Hi, my name is Steve Blyle, and I'm a welder. From fabrication and repair shops to backyard garages, arc welding is one of the most common and versatile methods of joining metal. This is the SMAW, or shielded metal arc welding process. Electric current from a welding machine produces an arc between the base metal and a consumable electrode, which is the welding rod. That arc burns the flux coating on the rod, creating gases that shield the weld area from coming in contact with oxygen in the air. The gases surrounding the arc are superheated, causing the base metal to melt, while the filler metal from the rod is being deposited into the molten puddle. Whether you're learning to weld to build something or make repairs, the first step is to learn how to consistently run a good weld bead. Before we start burning rod, though, there are a few things you should know about the equipment we'll be using. So let's begin with the welding machines. The job of a welding machine is fairly simple, and that is to provide a steady, controllable current to the electrode. Now, regardless of the size or shape, welding machines will provide either alternating current or direct current to the electrode. And this little machine gives you the choice of either AC or DC. The main advantage of alternating current is that it's easier to produce. They use simple transformers, so you generally get more power for your money. This one will give you 225 amps on AC, but only 150 amps on DC. If you think about alternating current, the electrons are moving back and forth, and at the point where the electrons change direction, the flow or current actually stops. Certain welding rods have been designed with stabilizers in the flux to help maintain and control the arc through these amperage lags. So if you're using a welding machine that provides alternating current to the electrode, you want to make sure to use a welding rod designed for alternating current. Most welding shops and professional welders use machines that provide direct current to the electrode. And in my shop, I use a 250 amp DC machine. Direct current provides a steady flow of electrons in one direction. The polarity, or direction of flow, is determined by how the leads are connected to the positive and negative terminals on the welding machine. And many of the newer welding machines have a switch to choose the polarity. DC EP, or DC plus, is direct current electrode positive. The electrode is connected to the positive and the ground is connected to the negative terminal. Current is generally considered to flow from negative to positive, so with the electrode positive, the arc actually travels from the metal up to the welding rod. This causes the tip of the rod to superheat. For general purpose welding, all the common welding rods use DC EP with the electrode positive. DC EN, or DC minus, is direct current electrode negative. The electrode is connected to the negative terminal and the ground is connected to the positive. With DC EN, the flow is from the welding rod to the metal, so the rod stays cooler and the metal gets the heat. This is used with certain rods for high-speed sheet metal welding. When you're starting out, you'll probably be welding with a machine that's put in front of you. And basically, if it's in proper working condition, you can weld with it. Keep in mind, though, that welding machines will weld differently. Even two identical machines may not operate quite the same. So while you're learning to weld, try to use the same machine as much as possible. Welding leads are insulated copper wire and come in sizes like a number 4, 2, 1, and single-aught. The larger the number, the smaller the diameter. The size welding lead you need to use depends on how many amps you'll be using and how long the lead is. And welding supply stores have charts to determine the size lead you need to use. On the end of the main lead, I use a quick connect with about 15 feet of number 4 lead and the electrode holder. This is called a whip. The smaller lead is a little more flexible and easier to deal with. This is a 200 amp electrode holder. Larger ones like 250 or 300 amp are available if you're mainly using big rods with high amperage settings. But for general use, the 200 amp is more comfortable. And I usually call this the stinger. Another type of electrode holder is available where you stick the rod in and twist the handle. If you need the rod at a different angle, you can just bend it. You also need a ground clamp. And I use a quick connect here too, in case I need to add more lead. Now, the light from arc welding is extremely bright. You need filter lenses both to be able to see the molten weld puddle and to protect your eyes from getting burned. These are typically available from a number 8 to a number 14. The lower the number, the lighter the lens. From what I can tell, some people are more sensitive to this light than others. A number 8 filter lens is way too light. Industry recommends a number 10, and I use a number 9. The lens has to be dark enough to protect your eyes, but light enough so you can clearly see the weld puddle. If you're welding with big rods using high amperage, you may want a shade darker lens than normal. And if this filter lens gets chipped or cracked, replace it. To protect the filter lens from sparks or getting scratched, I use clear plastic lenses in front and in back. There's a gasket that goes in first to seal the lenses, and everything's held in place with a clip. After you install the lenses, hold the hood up to a light and check for leaks around the edges. When you start welding, check it again. If any light from the arc is leaking around the edges of the lenses, it'll burn your eyes for sure. Also, replace the clear lenses when they get dirty or scratched. Having a clean lens makes a big difference in allowing you to clearly see the weld puddle. Okay, the last thing we need are welding rods. So let's take a look at some of the common ones. Some of the more common welding rods for carbon steel are E6010, 6011, 6013, and 7018. And the numbers are written right on the rods. These numbers actually mean something, so let's take a look at E6010. The E designates an arc welding electrode. The first two numbers, in this case 60, indicate that the filler metal has a tensile strength of 60,000 pounds per square inch. Depending on certain conditions of the weld, you may get a little more or less, but it'll be close to that. The 70 and 7018 indicate 70,000 pounds per square inch. So the first two numbers indicate tensile strength, and tensile strength is the force it takes to pull it apart. The third number indicates the position the rod can be used in. A number 1 shows that the weld puddle solidifies quick enough so this rod can be used in any position, flat, vertical, horizontal, or overhead. A number 2, like in 7024, indicates that the molten puddle remains so fluid this rod can only be used in the flat position or for a horizontal fillet, which is more or less flat. The last two numbers together, here it's a 10, indicate the composition of the flux coating. And this flux is what makes the whole arc welding process possible. As it burns, a gas is created that purges the weld puddle, keeping the oxygen in the air from mixing with the molten metal, which could cause gas pockets in the weld bead called porosity. The flux also helps stabilize the arc, and it lifts impurities from the molten metal. When the flux cools, it forms a slag coating over the hot weld bead, providing more protection from the air. There isn't a magic welding rod that just does everything. You may find one that you like to use, and that produces good results. But basically, welding rods can be put into one of two groups, fast freeze or filler. The fast freeze rods, 6010 and 6011, have a strong arc force that provides deep penetration. A light flux coating makes the molten weld puddle clearly visible, and the weld puddle solidifies relatively quick, leaving distinct ripples in the finished weld bead. Filler rods, 6013, 7018, and 7024, don't penetrate as deep. They build up weld bead. A heavier flux coating covers the weld puddle, keeping it more fluid, allowing for a smoother finished weld bead. So where exactly do you use these different welding rods? 6010 is used strictly on DC plus and 6011 on AC or DC plus. The strong arc force of these rods can blow off rust and paint, making these a good choice for repairs or modifications where the metal can't be completely cleaned. Also, these rods are often used as a first pass to provide deep penetration or to fill gaps in fit-ups that are less than perfect, then covered with a filler rod. 6013 was actually designed for high-speed sheet metal welding on DC-, but these rods can also be used on AC or DC+ for general-purpose welding and light fabrication. With stabilizers in the flux, 6013 is probably the easiest of all the rods to use, and it produces a smooth finished weld bead. 7018 is a low hydrogen rod with iron powder in the flux. It's generally used on DC+, and an AC 7018 is also available. These produce the highest quality welds and were developed for situations where there's extreme stress on the weld joint. It can be used to weld some of the harder low alloy steels on cast steels, and when making heavier welds, the low hydrogen characteristics prevent the weld from cracking because of the expansion and contraction of the metal. Iron powder in the flux provides a high filler metal deposit rate, which means you can put more metal down faster. 7018 produces a smooth finished weld bead, but does require clean metal and a well-prepared joint. 7024 was used extensively in fabrication before wire feed. A heavy flux coating produces an extremely smooth weld bead, but these rods do require clean metal and a slightly higher amperage setting. 7024 can be used on DC+ or AC, and the 2 does indicate that this rod can only be used in the flat position. 6010, 6011, 6013, and 7018 are common rods and should be available everywhere. There are other welding rods, and they'll either be a fast freeze or a filler, with a different tensile strength, a slightly different flux covering, and usually designed for a specific purpose. Now, each of these rods has distinct characteristics, but there are some basic fundamentals that are common to all of arc welding. We'll start with the fast freeze type rods because the light flux allows you to see the molten weld puddle clearly. The fast freeze rods 6010 and 6011 are similar, and the same techniques can be used with either one. 6010 on DC+ might freeze or solidify a little quicker. 6011 with either AC or DC+ may be a little easier to use because of the stabilizers in the flux that help maintain the arc. Let's start by watching a weld, and I'll try and describe what to look for. After scratching the rod against the metal to make contact, the tip is held about 1/8 of an inch or 3 millimeters off the surface. This creates a gap for the arc to cross, and that's where the bright light comes from. While you're welding, don't watch the light. Look past it, through the smoke and sparks, and focus on the molten puddle of metal behind the rod. Welding takes a little practice, but it's not very difficult. Let's go through this step by step. First of all, you need to pay attention. This is ready to go. Anytime the tip of the rod touches the metal, it will arc. Okay, you want to get comfortable. Welding rods burn for about a minute, and it's a long ways out to the tip of the rod. So get comfortable and relax. Rest your arm on the table and use both hands on the stinger so you can be as steady as possible. When you're all set, either reach up and flip your hood down, or you can adjust the knobs on the side to flip the hood down with a nod. Starting the arc is like lighting a match. Drag the rod right against the metal. When it lights, bring the tip up and move back to the start. A scratch start gets the flux burning, forming the gases that purge air away from the molten puddle. To avoid leaving arc burns all over the metal, try to scratch right where you intend to weld. I usually hold the stinger with my thumb on the release lever. If the rod ever sticks, just open the stinger, then go back and break the rod off. If you're relighting a rod, the flux may be broken off a little at the tip. A scratch start will burn off that tip before you start depositing metal. Once the rod is burning, you need to start the puddle, giving the molten filler metal a little extra time to fuse to the base metal. This doesn't take long, only 2 or 3 little circles. Also, as the weld progresses, the base metal will heat up, causing the molten puddle to spread out. Start the puddle wide enough to keep the weld bead a uniform width. During the weld, the tip of the rod is held up off the metal. This is called the arc gap. Having control of this arc gap is one of the first and may be the most important thing you need to learn. As you're moving along to build weld bead, the rod is being consumed, so you also have to be moving in. And the whole time you need to maintain a constant, uniform gap between the tip of the rod and the base metal. If the tip of the rod is jammed right down on the metal, the arc doesn't have time to heat up the base metal. The weld bead kind of squirts out the back, not tying in well on the sides. If the arc gap is too long, the arc itself can jump around. Penetration will vary and you lose control of how the filler metal is deposited. Maintaining a constant arc gap is the first step to controlling the molten puddle and producing a uniform weld bead with consistent penetration. The better you learn to control that arc gap, the better you'll be able to weld. When the arc crosses the gap, it melts the base metal, forming a molten puddle. That arc stream also carries the filler metal from the rod into the puddle. This is a 60-10 weld bead that I pulled out of quickly. The leading edge of the puddle was actually below the surface of the metal. The strong arc force of 60-10 and 60-11 penetrates deep into the base metal and pushes the molten puddle back, building up weld bead. While you're welding, watch the sides, right where the weld buildup meets the surface of the base metal. For building up weld bead, either a circular or zigzag motion is commonly used. With a circular motion, as you ease the puddle over, watch the edge. When you bring it across, watch the weld build up, then the other side, and just ease the puddle around and around. A side-to-side or zigzag will produce nearly the same weld bead. Watch the outside edge, the weld build up, and the outside edge every time you cross. Something you want to keep in mind is that molten metal will follow the heat. Whenever you move the puddle across, while you are adding filler metal from the rod, molten metal is also following from the side. If enough metal isn't put back there when you come around again, you'll leave undercut. Undercut is a void or groove along the edge of the weld bead that's below the surface of the base metal. You can avoid this by always watching the outside edges to make sure the puddle is filling in and tying in at the surface. There's an arc force at the end of this rod that we can use to help manipulate the weld puddle by angling the rod. Think of it more like pushing the puddle instead of dragging it. Generally speaking, the straighter up and down you hold the rod, the less weld buildup. As you angle the rod, the more the weld bead will stack up. When the rod is held straight up and down, all the heat is concentrated right under the rod, and the arc force drives the puddle down. This results in deep penetration and spreads the puddle out for a flatter weld bead. As the rod is angled, the arc force is directed more to the back of the puddle, allowing the weld to build up. If the rod is angled too low, the arc is directed right where you're trying to build weld, making the puddle hard to control. You will run into situations where you may want to flatten out the weld, or you'll need to push the puddle back more, so you'll use different rod angles. When you're starting out, an angle somewhere between 45 degrees and straight up and down is comfortable, allows a good view of the puddle, and works well for building weld bead. The rod size is the diameter measurement of the metal in the electrode. Common sizes are 332, 1/8, and 532. Most welding rod size charts, where they give the metal thickness to the rod size and amperage setting, are generally from the point of view of maximum weld in minimum amount of time, often not taking into account the welder's ability or different welding situations. You can always use a smaller diameter rod for better control. It just takes a little longer to build up weld bead. This is a 1/8 E6010 electrode, and this is the most common size used. The manufacturer's recommended amperage setting is from 75 to 130 amps. They're saying this rod will work over a 55 amp range. The specific amperage setting is considered a variable and depends on metal thickness, position of the weld, and the welder's ability. The whole purpose in arc welding is to get the base metals hot enough to melt, forming a molten puddle. If the amperage is set too low, the base metal doesn't get hot enough, and the puddle looks like it's following the rod around. If the amperage is set too high, the base metal gets too hot. The stronger arc force gouges deep into the base metal and pushes the puddle back. When the amperage is set about right, the puddle will spread out and the outside edges tie in immediately. You can ease the puddle around, kind of pushing it with the movement of the rod. Depending on each welding situation, the amperage setting can change. Thicker metal dissipates the heat, so you need a little more amperage. Thinner metal will get hot fast, so you can use a little lower amperage. The final amperage setting is determined by what the molten puddle is doing. You do need a place to start, so try about the middle of the manufacturer's recommended range, and don't be afraid to go up or down a little bit. Welding really is about the temperature of the base metal, so we can't talk about the amperage setting without looking at the speed of progression, or travel speed. The faster you move, the less time heat is put to the base metal, so it stays cooler. When you move slower, you're putting the heat to it for a longer amount of time, so the base metal gets hotter. When you move too fast, the metal doesn't have time to heat up, so the weld bead just skates across, not getting any penetration. If you move too slow, the metal gets extremely hot, causing the puddle to spread out, making it hard to control. When the travel speed and amperage setting match, the puddle spreads out, but it's still controllable. The sides tie in and the weld builds uniformly. As you gain more control of the rod, try using a slightly higher amperage setting and increasing the speed of travel. The higher amperage setting provides better penetration and a smoother finished weld bead. Try to weld as hot as you can control the molten puddle. To finish a weld bead, add a little extra metal before you pull out, to avoid leaving a crater that's below flush with the surface of the base metal. Circle the rod once or twice, then bring the rod up and back over the weld. While different rods may not look quite the same, these are the basic steps for all the welding rods. Scratch to get the arc going. Start the puddle wide enough to keep the weld a uniform width. Maintain a uniform arc gap with an amperage setting high enough to let the puddle spread out. Ease the puddle around using the force of the arc and watch the sides and the weld build up. Add some filler metal before pulling out over the weld bead. That's about all there is to it. For 60-10 in the flat position, try a circular motion and angle the rod to build up weld. Watch the molten puddle, not the light. Keep the circles tight for a smoother weld bead. A zigzag motion will produce about the same weld. Watch the edges to make sure they're filling in and ease the puddle back and forth. Because of the strong arc force and light slag, you can also use a whip or step motion, and this is what makes the fast freeze rod so versatile. The tip of the rod is moved back so the arc is actually brought out of the puddle. Then molten metal is pushed back in. With the step motion, watch both sides and the weld build up every time you push the puddle in. This kind of rod movement can be used for deep penetration by digging down on the backstroke, then filling the gouge in. On thinner metals, where you don't need a lot of penetration, you can puddle, then long arc to let the weld bead cool, and puddle again. The thinner the metal, the faster this goes. The step motion can also be used to fill gaps in poorly fit joints. Keep the rod deep in the gap and bring it back, allowing the metal to cool. Then push a little more metal in to fill the gap and let it cool again. The step motion may not always look real slick, but it's usually covered with another pass. So far, we've been welding in the flat position. For a vertical with 60-10, you can run either uphill or downhill. Downhill is easier, but there's less penetration and weld buildup. Because heat rises, you're welding away from the heated metal, so you can use a slightly higher amperage setting. Watch the sides and the weld buildup. Try a circular, zigzag, or step motion and angle the rod up a little so the force of the arc helps hold the puddle up. With a circular motion, keep a steady arc gap and ease the puddle around. Move fast enough to stay ahead of the molten puddle. If the puddle wants to drip down, try moving faster, or maybe even a slightly higher amperage setting. When you weld uphill, you'll be welding into the heated metal, so turn the amperage down a little. Angle the rod up so the force of the arc doesn't blow the puddle out. An uphill weld really gouges into the base metal, making undercutting a potential problem. So pay particular attention to the sides of the puddle and watch the weld buildup underneath the rod. If the base metal gets too hot, the puddle may fall out, or you might burn a hole right through the metal. Mess with the amperage setting and your travel speed until you can carry that puddle right uphill. A horizontal weld is a cross, and you want to angle the rod to push the puddle up. Keep the rod nearly perpendicular to the metal or angle into the weld a little bit. If you angle the rod too far, the arc force can blow the puddle out. Using a circular motion, keep a steady arc gap and just ease the puddle around. Every time you bring the rod down, the molten metal will follow the heat. Make sure you push the puddle up and watch the top side. If the bead is wanting to sag down, try a faster travel speed to keep the base metal cooler. That leaves us with overhead, straight up and down. Overhead is about the same as welding flat, just a little more awkward. The real challenge is to find a comfortable position so you can keep the rod steady. Your welding hood should have an adjuster to help hold it up, so you don't have to bend your neck back so far. Now, believe it or not, the molten puddle doesn't want to fall out. Unless you blow it out with the arc force, the molten metal wants to stay with the heat. It likes the heat. Hold the rod nearly straight up and down or angled slightly in the direction of travel, away from the weld. Try a circular motion and just make the puddle look the same as when you're welding flat. All the sparks will be coming your way, so wear protective clothing like a leather coat, some good gloves, and I like to cover my ear with a hat. Getting burned is a little distracting when you're trying to run a good weld bead. 60-10 and 60-11 won't give you a smooth finished weld bead, but they do provide deep penetration in weld joints and when making repairs. 60-13 welding rods were developed for welding sheet metal on DC-. The rod is held perpendicular to the metal with a tight arc, and the travel speed is as fast as you can go without having the weld bead skip. Today, 60-13 is more often used for general purpose welding with AC or DC+, and it is a good rod for the small, low amperage welding machines. One of the first things you'll notice about 60-13 is that there's a heavier slag coating on the weld bead. The slag even covers the top edge of the weld puddle. This keeps the puddle more fluid, helping to produce a smoother, finished weld bead. Typically, 60-13 is available in 332, 1/8, and 532. 1/8 is the most common size used, and try starting with an amperage setting around 130 amps on AC or 115 amps on DC. Because of the slag covering, the differences in the appearance of the weld are a little more subtle, but when the amperage is set too low for the situation, the puddle will follow the rod around, taking longer to tie in on the sides. The heavier slag may even interfere with the arc. If the amperage is set too high, the molten puddle and slag are extremely agitated and remain molten longer. When the amperage is about right, the weld puddle spreads out, tying in and moving easily with the motion of the rod. In the flat position, you can run straight or try a little side-to-side motion. Angle the rod somewhere between 45 and 90 degrees to build up weld bead. Scratch start the puddle, and maintain a short arc gap, even to the point of lightly resting the tip of the rod on the metal. Watch the puddle. The slag covers the top edge, but you can still get an idea of the weld buildup. Watch the sides to keep the weld bead straight, and just ease the puddle side to side. On vertical welds, 6013 was designed for a downhill application. You'll be welding away from the heat, so try turning the amperage up 5 to 10 amps. Angle the rod up so the force of the arc helps hold the puddle up. Maintain a short arc gap and try a slight side-to-side movement. Watch the outside edges to keep the weld bead straight and travel fast enough to stay ahead of the molten puddle. If you can't stay ahead of the molten puddle coming down, try moving a little faster or raising the amperage setting. For more weld buildup on heavier metal, 6013 can be run uphill. Start by turning the amperage down 5 to 10 amps. Try using a side-to-side motion, moving up fast enough to keep the puddle from dripping down. Make sure the sides are filling in to avoid leaving undercut. To make a horizontal weld, angle the rod up to help push the puddle up. Keep the rod nearly perpendicular to the metal or angled back into the weld just a little. Maintain a short arc gap and constant travel speed to produce a smooth weld bead. The molten slag will run down, covering the bottom, but watch the top side of the puddle. Move fast enough to avoid excessive weld buildup. While you're learning to weld horizontally, don't try to carry too much metal. Keep the weld bead small. If you need more weld, you can always run a second pass above the first one. Overhead with 6013, like every other type of welding rod, is awkward. Hold the rod straight up, or, because of the mild arc force, you can angle it back into the weld a little bit, and try a slight circular motion. The heat of the weld is going straight up, right where you want it. So if you can get in position to maintain a short arc gap and uniform travel speed, overhead will produce a good weld. 6013 is the favorite rod in many home shops. They're easy to light, they maintain the arc, and produce a good-looking finished weld bead. 7018 produces an extremely high-quality, good-looking weld bead. This is the rod to use for heavier fabrication and repair or any situation where there's stress on the weld joint. These rods rely on a heavy slag coating to protect the molten weld puddle from coming in contact with oxygen in the air. This heavy slag makes 7018 run a little different than the other rods we've looked at. With the fast freeze rods, 6010 and 6011, the molten metal in the weld puddle is completely visible. Slag covers the top edge of the molten puddle with 6013, but the filler metal and slag solidify pretty much at the same time. With 7018, the entire weld puddle is covered by molten slag. The filler metal actually solidifies underneath, while the slag stays molten on top. If you keep in mind that what you see is molten slag and understand what the metal is doing underneath, 7018 is fairly simple to use. And even though the metal is solidifying underneath, watching the molten slag behind the rod will give you an idea of the weld buildup. 7018 is a little more sensitive to arc gap and rod movement. Make sure you're comfortable so you can be as steady as possible. A scratch start will get the flux burning before you deposit any metal. If you're relighting a rod, there's usually slag covering the tip. You may have to bump the rod to break that slag, then scratch to get going. Once the rod is lit, start the puddle. Besides tying in and getting started wide enough, this gives a little extra time for the gases to cook out of the molten puddle. If you move too quick, gas pockets may cause voids in the weld bead called porosity. Most times they're not even visible until you grind into the weld bead. Porosity can also be caused by welding on metal that's rusted, painted, or has any contaminants on it like oil or grease. 7018 does require clean metal. After the puddle is started, try a little side-to-side motion, maintaining a constant short arc gap. In some situations, you can even lightly rest the rod on the metal. With a mild arc force and slag covering the puddle, you do want to avoid letting the rod burn up or pulling the rod away from the metal. You don't want to let that slag cool, so keep the arc in the puddle. The typical rod sizes are 332, 1/8, and 532. Because the flux contains iron powder, which deposits more metal in the weld puddle, 7018 requires a little higher amperage, and these settings may vary up or down depending on metal thickness, weld position, and your ability to control the movement of the rod. With molten slag covering the entire puddle, you depend more on how the puddle acts than how the puddle looks. If the amperage is set too low for the conditions, the puddle won't spread out, taking longer to tie in on the sides. The rod might stick or go out. If the amperage is set too high, the puddle is agitated and extremely fluid. Little balls of metal might dance off to the sides, causing excessive weld spatter. When the amperage is about right, the slag solidifies back from the rod. The sides tie in, and you can ease the puddle side to side. Here again, as you gain control of the arc gap, rod movement, and travel speed, you'll find that 7018 runs easier and cleaner with the amperage set a little to the hot side. The angle of the rod not only affects how the filler metal is deposited, but how the molten slag will behave. If the rod is held straight up and down, the slag can get in front of the weld puddle. If the rod is laid too far down, the flux coating won't burn evenly and the rod may stick. When the rod is angled between 45 and 90 degrees, the slag is forced back where it belongs, over the molten filler metal. Welding in the flat position is fairly simple. Remember to relax, get comfortable, and use two hands on the stinger. Try to maintain a short arc gap and constant travel speed. Watch the outside edges of the puddle to make sure they're fusing and staying even. Look behind the rod for an idea of the weld buildup. In the flat position, even 532 rods are fairly easy to control if your welding machine can produce enough amperage and there's plenty of metal to carry the heat. For a horizontal, we'll be welding across. If you're just starting out, try using a 332 rod. The smaller puddle is a little easier to control. Normally, I weld from left to right because I can see the puddle better. For 7018 in a horizontal, I move from right to left. You can weld in either direction, whichever is more comfortable. Angle the rod up and back into the weld a little. The puddle is fluid, so keep moving to avoid excessive weld buildup. Molten slag will cover the bottom, but watch the top side to keep the bead straight and avoid undercut. If the weld bead wants to sag, try increasing the travel speed. You want to go slow enough to let the molten metal fuse, but fast enough to keep the base metal from overheating, which causes the puddle to get more fluid and sag. Vertical welds with 7018 are made uphill. Start at the top and scratch down to where you want to start the puddle. You can run straight up or use a side-to-side movement. When I do this, it feels like there's a slight arc in the motion. Move across the center relatively quick. As soon as the puddle ties in on the side, cross back and keep on going. The amperage setting and travel speed go hand in hand, especially when you're going uphill. Maintain a constant short arc gap Don't let the rod burn away, and don't jam the rod into the puddle. As you gain experience, you can carry more metal, but try starting out with a 332 rod and keep moving. You don't want the base metal overheating, which is the main reason the puddle falls out. Overhead with 7018 produces an excellent weld. The heat is going right where you want it. Try about the same amperage you'd use for welding flat and hold the rod nearly straight up and down or angled slightly into the weld. You can run straight or try a little side-to-side motion to carry more metal, and you can carry quite a bit of metal overhead. Get comfortable and be creative if you have to. When you can control the rod movement, that metal will stay up there. However, because the slag remains molten longer, the slag can drip. I usually wear a leather welding jacket for overheads. You will be right underneath the weld. 7018 takes a little more practice, but it's well worth the time to learn how to use this rod. Well, that's about it. I hope I've given you an idea of what to do and what to look for to run good weld beads. As you're welding, concentrate the whole time you're burning that rod and focus on the molten puddle. Do whatever it takes to make that puddle do what you want it to do. There isn't anything automatic about arc welding. You need to put that metal where it belongs and learn to see the weld as it's going in. When you're done, inspect every weld you make. If what you did worked, do it again. If it didn't work, try something different. A smooth, uniform weld bead will come with practice, but you do want the sides of the weld to be tied in nicely to the base metal. If the sides aren't tied in, you may be moving too fast, jamming the rod into the puddle, or running too low of an amperage setting. Moving too slow will overheat the base metal. Long arcing will produce an inconsistent weld bead with excessive spatter. Everybody welds a little different, so watch other welders if you get the chance, and develop a style and rhythm of your own. Practice with different types and sizes of rods, and remember, arc welding is about making one good weld bead at a time. Hi, my name is Steve Blyle and I'm a welder. Whether you're headed out to work in the welding industry or out to your home shop, the goal in welding is the same, putting two pieces of metal together so they stay together. There are many variations and options in joining metal, not only material thickness, weld position, or strength requirements, but also individual techniques and skill levels. Every weld joint is made one weld bead at a time, so let's review some of the basic fundamentals. Whether your welding machine is electric or portable, the power source will provide either alternating current or direct current to the electrode. Alternating current flows in both directions, creating an amperage lag. Certain welding rods have been designed with stabilizers in the flux to help maintain the arc through these lags. Direct current welding machines provide a steady flow of current in one direction. The direction of flow, called polarity, is determined by how the leads are connected to the welding machine. DC plus with electrode positive is the polarity typically used for shielded metal arc welding. All the common rods used for welding on carbon steel have characteristics that make them better suited for different situations. The fast freeze rods have a strong arc force that helps burn off surface impurities. A circular or side-to-side motion can be used to build up weld, or because of the light flux coating, these rods can be stepped to provide maximum penetration. In the vertical weld position, 6010 and 6011 can be run either uphill or downhill. These are good rods for tacking up weld joints, welding metal that is slightly rusted, filling gaps in poorly fit joints, and as a first pass for good penetration. The filler rods don't penetrate as deep. They build up weld. Stabilizers in the flux make 6013 one of the simplest rods to use. With a slightly heavier slag covering, try to keep the arc in the puddle. 6013 can also be run either up or down on vertical welds. For general purpose welding, 6013 produces a smoother finished weld bead. 7018 contains iron powder in the flux and low hydrogen characteristics. Except for directly under the arc, a heavy slag covers the entire weld puddle. Either running straight or with a side-to-side motion, the arc needs to be maintained on the leading edge of the puddle. In the vertical position, 7018 is run uphill. 7018 requires better rod control, but does provide the strongest welds for heavy stress situations and also the smoothest welds for ornamental type projects. Welding rods are available in different amounts, and it's a good idea to have both fast freeze and filler rods on hand. Cover yourself up, wear some good gloves, a hat, keep clean lenses in your welding hood, and always wear safety glasses. Before you light the rod, get comfortable. Scratch to light the arc. Bring the rod back and start the puddle. Maintain a uniform arc gap with the amperage set high enough to let the puddle spread out. The molten metal follows the heat. Make sure you're filling in along the edges to avoid undercut. Add a little extra metal to the puddle before pulling out back over the weld. You should always examine the finished weld bead for any defects, but really, you need to see the weld as it's going in. This is a totally manual process. You have to control the heat and filler metal during the weld by watching and understanding the molten puddle. Look past the rod and the light, focusing directly on the molten pool. Watch the edges and the weld buildup, constantly analyzing how it's flowing out and how fluid it is, making slight adjustments when necessary. The amperage setting, which regulates the amount of current flowing through the rod, is the main control of the heat available to the weld. When the amperage is set too low, the puddle only forms under the rod. Increasing the amperage generates enough heat to form a molten pool. Along with starting to get penetration, this is where you begin to have control of the edges of the puddle and the weld buildup. There isn't an exact amperage setting here. In fact, this is one of those things that welders see differently. Also, as the metal thickness or weld position changes, the amount of heat required will be different. Watch the puddle. You're looking for it to flow out to the sides of the rod. When the amperage is increased more, the molten pool penetrates deeper and spreads. Eventually, the filler metal becomes so fluid and agitated you can no longer control it. Experiment with the amperage setting. For good penetration and smoother welds, you want the amperage set as high as you can while keeping the molten metal from becoming too fluid to handle. Because of the characteristics of the flux coating, the puddle will look different depending on the type of rod you're using. The entire puddle is visible with 6010 or 6011. Slag covers the top rim of 6013, but the molten metal is still visible on the sides, and the puddle should move easily with the rod. With 7018, slag covers the entire puddle, but you still want to see it flowing out to the sides, with the slag solidifying back from the rod. During the weld, the filler metal is actually solidifying underneath while the slag stays molten. In the horizontal or vertical position, the slag can run or drip. Don't let this fool you into thinking the weld is too hot. You'll probably need to experiment more to set the amperage for 7018, but you will get better results running a little to the hot side. Regardless of which rod you use, the amperage only provides the heat. The rod angle determines how fast the metal will heat up. When the rod is held more perpendicular, the molten pool forms and spreads quickly, allowing a faster travel speed to limit penetration on thinner metals, deposit less metal for a smaller weld, or flatten the bead in a bevel. As the rod is angled, some of the heat is taken off the metal. A slower travel speed can be used to build up a crowned weld bead. If the rod is angled too much, the metal won't get hot enough. The molten pool will narrow, the bead will stack up, and you'll lose control of the edges of the puddle. On most weld joints with a good fit up, You want to maintain a consistent rod angle to produce a uniform weld bead. In some situations, though, you may need to vary the rod angle during the weld. To fill a gap in a weld joint, the rod can be angled more, slowing down to deposit more metal, keeping the build-up uniform, then angled back up to finish the weld. Controlling the rod angle takes a little practice, but you need to stay loose and relax. Whether you're holding the rod up to flatten the bead or angling it to build up weld, you want to travel at a speed that keeps the molten puddle the same size. Watch the puddle. If the travel speed is too fast, the metal doesn't have time to melt, so the puddle narrows. If the travel is too slow, the metal gets hotter and the puddle spreads. Depending on the rod, the filler metal may flatten out or stack up and roll. Always maintain the size of the puddle with the travel speed. Last is the arc gap, which is the distance from the tip of the rod to the metal. Shielded metal arc welding machines use a constant current power source. The amperage is set with the voltage varying to maintain the arc. You want to avoid jamming the rod right down against the metal or long arcing too far, but you can use slight variations in the arc gap to help control the heat and shape the weld. This is difficult to measure, but a medium arc length is used to build up weld. Shortening the arc reduces the heat, cooling down the weld puddle. Try using a shorter arc gap on vertical up with 70/18 when you want to build up more weld. Slightly lengthening the arc causes the heat to increase, spreading the puddle out, and is used with a more perpendicular rod angle for making smaller beads or flattening the weld on heavier metal. It is important to be consistent though. Varying the arc gap during the weld changes the heat, making it difficult to maintain a uniform weld puddle. When you start looking at all the aspects of running a weld bead, there are many possibilities. That's why everybody welds a little different. Practice and experiment, trying to make that puddle do what you want it to do. Watch other welders if you get the chance, but in the end, you need to see the weld puddle at the end of your rod and develop a style that works for you. We've been looking at heating the metal to allow the molten pool to penetrate and fuse. All that heat also has an effect on the base metal itself. Metal is made up of groups of atoms bonding together to form grains. When metal is heated past a certain temperature and cooled quickly, smaller grains are formed, making the metal harder. Cooling the metal slowly allows more atoms to bond, forming larger grains, which makes the metal softer. In welding, the metal adjacent to the weld bead becomes hot enough to change the structure of the grains. Because only a relatively small area is heated, the metal cools quickly, forming smaller grains and becoming harder right alongside the weld. Welding also causes the pieces of metal in the joint to draw. Heated metal expands, so during the weld, the molten filler metal is deposited in its maximum expanded state. As it cools, it contracts. When the metal is free to move, it will draw in the direction of the weld. If the pieces being welded are trapped, the molten weld metal still contracts, leaving some residual stress in the metal. There isn't any way to stop this. The metal is going to move. Whenever possible, weld on both sides to reduce the draw, and on pipe or square tubing, use a sequence of welds to help control the draw. Extreme differences in temperature do have a greater effect on the metal. If it's freezing cold, use a torch to heat the metal up a little. Condensation will appear, and just warm it up until the moisture dries. Also, if you are welding on harder, higher carbon steel, which does not handle expansion and contraction very well, a preheat may be necessary to prevent the weld from cracking as it cools. As always, there are a lot of variables, the type of steel and the stress that will be put on the finished product. In most cases, projects are designed so that the stress put on the weld joint does not come anywhere close to the maximum strength of either the metal or the weld. Try to complete the weld once you start it and avoid building up more weld than necessary. When you're finished, let the metal cool slowly. If the metal does break next to the weld, you may need to take a closer look at the thickness of the metal being used and the overall design. Okay, let's take a look at putting two pieces of metal together. first steps with any type of weld joint are metal preparation and joint fit up. If you're working with new metal, most of the rods can handle the mill scale, which is a dark layer on the surface. Use a grinder to clean any metal that's rusted or painted. Impurities on the surface can cause porosity, lack of fusion, or even interfere with the arc. When you're cutting metal, keep the edges straight and square. If you use a torch, chip or grind off any slag left from the cutting process. During fit up, use good tacks to hold the pieces together, and if you're leaving a gap, keep it uniform. Irregular gaps in the joint not only take longer to weld, they make it way more difficult than it should be. You can avoid a lot of problems by cleaning the metal and taking your time on fit up. While there are many variations of weld joints, there is generally considered to be 4 types: butt joints, lap joints, T-joints, and corner joints. On a butt joint, the weld should penetrate deep, with the amount of weld deposit at least equal to the thickness of the metal. For maximum strength, 100% penetration welds are used to completely fuse the edges. On a lap joint, the weld is called a fillet, with the legs coming up and out a distance equal to the thickness of the metal and the weld slightly crowned. A fillet is also used on T-joints, where the edge of one piece is joined to the surface of another. Welding on both sides reduces the amount of weld necessary and overall produces a stronger joint. Corners are joining the edges at an angle, with metal preparation or fit up allowing for sufficient penetration and weld deposit. Let's start with butt joints, and this can be on plate, flat bar, angle iron, pipe, or square tubing. When the metal is around 1/8 of an inch thick, keep the edges straight and square for a perfect fit. You'll generally get good enough penetration just butting the pieces together, especially if you can weld on both sides or all the way around. On plate or flat bar, tack right on the outside edges to help carry the heat. For square tubing, tack the corners, then weld opposite sides from tack to tack. If you intend to grind the weld off for a smooth finish, you can leave a very slight gap, but keep it uniform. Whenever possible, start at the outside edge and weld towards more metal. In the flat position, hold the rod fairly perpendicular to the metal. You can weld with 60-10 or 60-11 using a circular motion. Turn the amperage down a little, but you're going to have to travel faster to control penetration and avoid burning through. For a smoother finished bead, try 60-13 or a 3/32 70-18 with a side-to-side movement. On a horizontal, hold the rod nearly perpendicular to the weld. Watch the puddle. With 60-10 or 60-11, adjust the travel speed to let the puddle spread out without overheating the metal. Watch the top side to avoid undercutting. With 60-13 or 70-18, try running straight without any rod movement, maintaining a uniform arc gap and travel speed. If you can position the joint, butt welds on 1/8 metal are easier welded vertical down. 1/8 metal is fairly thin for stick rod, so use some practice metal to figure out the amperage and adjust your travel speed. Starting at 3/16 of an inch, you want to bevel the edges to allow for good penetration. Bevels are generally around a 30-degree angle with the top edge straight and a flat spot called a landing on the bottom. Hold the grinder at a slight angle, using the bottom corner of the disc to take off metal. When you have it close, hold the grinder flat to smooth the bevel and straighten the top. On heavier metals, it may be easier to cut the bevel with a torch, then finish it with a grinder. The reason for beveling the edges is to control the puddle deep in the joint. If the bevel isn't wide enough to get the rod into the bottom, you can always take the grinder up on edge, slightly cock, and use the curve of the disc to open the bevel up a little more. A beveled butt weld can be divided into 3 parts. The root, which is the first pass fusing the bottom of the joint, the filler, and the cap. There are several options in fitting up butt joints, and the main difference is how the root pass is welded. The bevel pieces can be fit up with a small gap, allowing the first pass to penetrate as deep as possible. For 100% penetration, either a backup bar is used, with the first pass fusing all 3 pieces, or the metal is fit up with a gap, and the root fuses the bottom edge and actually builds weld on the back side. After the first pass, filling and capping is basically the same, so let's take a closer look at getting the joint started. Anytime you weld in a bevel, you want to hold the rod fairly perpendicular to the metal to flatten the top of the bead. If you angle the rod, the weld bead will crown, leaving slag that may get covered on the next pass. You also want the weld buildup even. Use a grinder to knock down any high spots from stopping and starting. It's a lot easier to keep it uniform with a grinder than to try to fix it with the next weld bead. Also, if the bead does crown in the bevel, use your grinder to knock off the top to avoid trapping slag. Not all welding situations require 100% penetration. That depends on the type of stress placed on the joint. But you always want to bevel the metal, leaving at least a small gap. 60-10 or 60-11 will provide good penetration, and for the first pass are a little easier to deal with in any of the weld positions. You can use a whip or step motion, gouging into the metal for penetration, then pushing the puddle in to fill. Watch both sides to avoid undercutting along the edges. For more weld buildup, try using a modified circular motion, always coming back to the leading edge of the puddle in the bottom of the joint. If you can handle the puddle, you can also use a filler rod. With 60-13 or 70-18, hold the rod fairly perpendicular. Use a slight side-to-side movement and avoid jamming the rod into the sides. Depending on the bevel and gap, you may need to follow the metal to maintain a uniform arc gap. The base metal is getting thicker as you come up the bevel, taking more heat. During the weld, you want to see the edges of the puddle flowing out and tying in on the sides of the bevel. After the first pass, chip the slag, clean it with a brush, and you're ready to fill and cap. If you can get to both sides of the metal, you can weld the backside for a stronger joint. Grind down to clean metal, keeping the depth and width uniform. With the rod angled a little more, slow the travel speed and build up welds slightly wider than the groove and above flush with the surface. Some welding situations require complete penetration for strength. If the pieces being joined do not fit up perfectly, or with some grades of hardened steel that tend to crack on the first pass, a backup bar is used. A V-bevel with a backup bar is also the procedure for structural welding tests. The goal is to melt and fuse the bottom edges of the pieces being joined to the backup bar. Prepare the bevels with slightly less of an angle and a feathered edge. Grind off the mill scale on the backup bar. Only a narrow strip is going to get tied in, and you don't want surface impurities taking the heat. Fit the backup bar tight with around 1/4 inch gap. This type of joint is generally welded all the way with at least a 1/8 70-18, and you have to be able to get the rod all the way to the bottom. Either tack up on the backside, staggering the tacks, or in the bevel. When you tack in the bevel, grind the starts and stops thin. Always keep in mind, along with fusing the pieces at the bottom, you also want the top of the weld relatively flat to avoid trapping slag. In the flat position, hold the rod nearly straight up and down, angled slightly back towards the weld. Keep the arc on the leading edge of the puddle. With a slight side-to-side movement, pay attention to the arc gap. You want to see the edges of the molten pool tying into the sides of the bevel to avoid crowning the bead. When you're using 70-18 in a bevel, stay ahead of the weld buildup and slag. If molten slag is pushed in front of the rod, it can interfere with the arc or limit filler metal fusion along the sides. On vertical up welds, you won't have any problems fusing the base metal to the backup bar. You do want to keep the weld bead flat without undercutting along the edges. Keep the rod fairly perpendicular to the metal, angled up slightly. The puddle needs to flow out on the sides for a flat weld bead and to avoid undercutting. Travel up fast enough to keep the metal from overheating, which causes the molten puddle to spill down. You may need to lower the amperage a little, maybe 5 amps or so, but don't lower it too much, as many problems are caused by running too cold on verticals as by running too hot. Remember, the amperage only provides the heat. It's the travel speed, rod angle, and arc gap that determine just how hot the metal is going to get. On overhead butt joints with a backup bar, you don't get to build up quite as much weld bead. With the rod nearly straight up and down, adjust the travel speed to let the puddle spread out without overheating the metal. Most of the problems with overhead come from not controlling the rod. When the tip dances around, varying the arc gap, the amount of heat at the weld is not uniform and focused. Find some way to steady yourself so you can control that rod. Also, if the rod is angled too far back towards the weld, the molten filler metal takes the heat instead of the metal, causing the puddle to drip. Horizontal is generally not used for welding tests, but you often get them in practical situations. Angle the rod up and slightly into the weld. The bottom bevel acts as kind of a landing, helping to hold the weld, so you may be able to use a slight rod movement. Watch the top side and push the puddle up. Set the amperage to allow a fast enough travel speed so the base metals don't overheat, which causes the puddle to become too fluid. Don't try to carry a lot of metal on a horizontal. Just get all the pieces tied together and keep the filler metal from sagging. The last type of root is in a V-beveled open butt joint. We're going to shove a 60-10 rod deep into the gap and run a weld bead on the back side of the metal. Preparation and fit up are more critical, so take your time getting the metal ready. The edge of the bevel needs to be straight and square. Grind off all the mill scale on the bottom side. A half-round file works good to clean up the inside of square tubing or pipe. The landing should be uniform. Use a file to knock down any high spots. With a 1/8 60-10, I use a 1/16 oxyacetylene welding rod as a spacer with around a 16th landing. The size of the gap and landing can vary a little, but when you figure out what you like, try to keep it consistent for every weld you make. Line up the bottom edges of the metal. With a spacer to adjust the gap, run one tack, pushing the rod right down into the gap. Before you finish tacking up, remove the spacer. As tacks cool, they contract and the spacer gets jammed up. So pull the spacer, make sure the gap is uniform, and finish tacking the joint. On heavier pieces, after the first tack, use a small wedge or a screwdriver to keep the gap uniform. Because of the taper, you can remove these after the joint is completely tacked. On square tubing, tack opposite corners. For pipe, opposite sides. Make sure the gap is uniform, straightening when necessary, then put in 2 more tacks. Flat, horizontal, overhead, and vertical down root passes are all done the same way. Grind the edges of the starts and stops thin. Hold the rod perpendicular to the metal. Scratch start right on the tack. Push the rod down into the puddle and start moving. The filler metal will squirt out the back until you hit the thinned out edge of the tack and it can poke through. Then move as fast as you can keep the gap filling in. If you're not getting all the way through, you will see filler metal squirting out behind the rod, back up in the bevel. Most of the light and sparks will be on the back side and you're building weld on the back of the metal. You want the amperage relatively high, so try starting about the same place as you'd run flat. If you do open a hole, stop right away, pulling the rod back over the bead. Restart right at the edge and keep going. When you finish the weld, grind the edges thin on both sides of the hole and fill it in. Some welding procedures require a vertical uproot pass, and generally, you'll need to run about 5 amps lower for uphill. The easiest way is to prepare the metal exactly the same, with a uniform narrow gap, shoving the rod in perpendicular and moving up as fast as the gap fills in. Some welders like to thin out the landing a little more, and with a step motion, rip a small keyhole, then fill it in, rip a hole, and fill it in, always keeping the rod deep in the gap. Other welders like to leave a little thicker landing and wider gap, here again using a step motion, laying metal in and making sure it's fusing on the bottom corners. The disadvantage to stepping the root is the possibility of undercutting along the edges on the back side. The advantage is that you actually see the root going in for 100% penetration. Stepping the root uphill also works well when the gap is uneven with wide or narrow spots. The backside bead should be above flush with the entire bottom edges of the bevels melted and fused. Any missed spots are called insufficient penetration. If the travel speed was too slow, the bead stacks up on the backside, causing excessive penetration. On the front side, because the rod was jammed right down against the metal, the bead will crown and undercut along both sides. Grind this out to avoid trapping slag. The metal will be thin from grinding, so you need to run another bead called a hot pass to add a little more metal and burn out any slag left behind. With 60-10, try stepping in the hot pass, not gouging quite as deep on the backstroke. Use a faster travel speed so you don't burn through, and watch the sides to avoid undercutting. You can also hot pass with a 332/70/18. Hold the rod fairly perpendicular. Carry the heat on the sides, moving across the center relatively quick. Don't try to build up a lot of weld, and make sure the sides of the puddle flow out so the top of the weld stays flat. Once the bottom of the joint is fused with any of these procedures, you're ready to fill and cap, and you will get better results using 60-13 or 70-18. If the metal isn't too thick, you may be able to finish with one more pass. On heavier metal, when more filler is required, remove all the slag between passes with a chipping hammer and wire brush. This comes with experience, but plan the weld. When several filler passes are required, overlap the edges of the previous beads if possible. The last filler pass should be slightly below flush. Try to leave the top corners of the bevel. With a slight side-to-side movement, pay attention to the arc gap. Don't jam the rod into the sides of the bevel. Keep the rod fairly perpendicular and the puddle flowing out to avoid crowning the bead. You may need to speed up or slow down to control the amount of filler metal deposit, but try to leave the top corners of the bevel. To cap the weld, angle the rod and slow down to build up a crown weld bead. Use the edge of the bevel as a guide to keep the sides of the weld straight. The finished weld should be as thick as the metal, so if you've penetrated deep, the cap only needs to be slightly wider than the bevel and above flush with the surface of the metal. Filling up more weld than you need doesn't add any strength, just takes longer and puts more heat on the metal. If the top of the bevel is too wide to cap with one bead, run 2 or more passes side by side to cap the weld. With a slight side-to-side movement, using the bevel as a guide, keep the outside edge of the first bead straight. Use the inside edge of the bead as a guide for the second pass. Adjust the travel speed and rod movement so the puddle flows out almost to the center of the first bead. The final pass will generally be smaller. Try holding the rod more perpendicular to the metal, running straight. Use a faster travel speed for less weld deposit. On a horizontal, angle the rod up slightly with a medium arc length. Try running straight without any rod movement. The first bead will help hold up the second pass, so hold the rod more perpendicular and travel fast enough to keep the bead from sagging. For the final pass, try angling the rod down slightly. Travel faster for a smaller bead. On verticals, you can either use small beads side by side or run a weave bead. Small beads are easier. Use the edge of the bevel to keep the first pass straight. Run as many beads as it takes, but try to leave the other side of the bevel for a guide to keep the final pass straight. If you're not limited to a maximum bead width by a welding procedure, you can try a weave bead. Start on one side, letting the puddle flow out to cover the edge of the bevel. Cross the center relatively quick to the other side and hesitate until the puddle flows out and covers the edge. Move the rod up a little, then cross, hesitate, move up, and cross. The upward progress is going to be slow, heating the base metal up more, so turn the amperage down a little. Use the edge of the bevel as a guide to keep the sides of the weld straight. For a smooth weld and straight edges, maintain a uniform arc gap and keep the upward progression tight. Weaving makes it possible to build up a lot of metal, but takes some practice to consistently produce a uniform finished weld bead. Whether you're filling or capping, you need to experiment with the amperage, rod angle, and travel speed, learning to control the amount of weld deposit and figuring out just how much metal you can carry without having it sag or drip. With the butt joint, we were joining the edges of the metal. When one piece overlaps the other, it's referred to as a lap joint. The edge, and especially the top corner, is going to get hot and melt faster than the surface, where the heat is being dispersed in all directions. You want to fuse the bottom corner while building up a full fillet with a slightly crowned weld bead. Lap joints can be welded all the way with a fast freeze rod, but the filler rods will produce a smoother finished weld. In the flat position, the weld is called a horizontal fillet, and you have two rod angles to consider, one in relation to the metal and the other to the weld bead itself. In relation to the metal, the rod angle determines the position of the fillet in the joint. The angle in relation to the weld controls the shape of the bead. Holding the rod perpendicular heats the metal quickly, spreading the puddle for a flatter weld. As the rod is angled back, the weld starts to crown. There are a lot of variables. You have to watch the puddle. With 60-10 or 60-11, hold the rod nearly perpendicular to the weld. With the arc on the leading edge, move the puddle into the bottom corner. Push it up to the top edge and bring the rod around to the leading edge. You may need to speed up or slow down to provide the heat, but always bring the arc back to the leading edge to fuse the corner. Watch the puddle flowing out to the top edge and tying in on the bottom. The fast freeze rods provide excellent penetration, but tend to produce a flat or concave weld. Even on thinner metals, it may take a second pass to build up a full fillet. The filler rods build up a smoother weld. Maintain a constant arc gap for a uniform weld bead, adjusting the travel speed and rod angle so the puddle flows out all the way to the top edge. Because the filler metal remains fluid longer, try running straight without any rod movement, keeping the arc on the leading edge of the puddle. On thicker metal, you may not be able to make a full fillet in one pass. You might be able to get it in two passes. The first one smaller and flat, then slowing down to carry more metal and crown the bead on the second pass. It might take 3 or more passes, and on heavy welds, use 70-18 to prevent the bottom beads from cracking. Put the first one in fusing the bottom corner. Chip off all the slag and wire brush the weld. Determine how far out the weld needs to be, and holding the rod straighter up and down, angled slightly back towards the weld, run a bead keeping the outside edge straight. Angle the rod more into the joint and perpendicular to the weld. Then run a second pass filling to the top edge. Overhead fillets really are like flat welds, just more awkward. Angle the rod into the corner with slight adjustments for different thickness metals. Keep the rod nearly perpendicular to the weld. Watch the puddle flowing out to the edge of the lap piece. As long as you keep the filler metal and base metal from overheating, that weld will stay right up there. On vertical lap joints, the outside corner is going to heat up a lot quicker than the surface. For vertical down welds, angle the rod up slightly. Carry the heat on the back piece. Move into the corner, pushing the puddle to the edge, then back out. Adjust the travel speed to stay ahead of the puddle and make sure you're on the leading edge of the puddle to move into the corner. You aren't going to build up a lot of weld on a vertical down, so you'll probably need to run a second pass. Vertical up with 70-18 will not only provide a stronger weld, you can also build up more filler metal in one pass. Always keep in mind that 70-18 is very sensitive to the arc gap. You don't want to jam the rods into the sides or long arc across the center. Carry the heat on the back piece. As soon as the puddle flows out, move into the corner, letting the filler metal flow to the outside edge, even pulling the rod out a little if necessary to maintain a uniform arc gap. Then back into the corner and across, slowing down to let the puddle flow out. Keep the upward progression tight and use a high enough amperage setting so you don't have to wait for the puddle to tie in. If you have any trouble running an uphill fillet with 70-18, try starting out with a 332 diameter welding rod. The smaller puddle is easier to control. You can also try stepping in a downhill pass of 60-10 or 60-11 first. This not only provides good penetration, it fills in the corner, making it easier to maintain a uniform arc gap for welding uphill. For heavier metal and more weld buildup, you can either stack weld beads side by side or use a weave bead. Lap joints in any position are fairly easy to weld. The outside corner will melt away, especially on thinner metal. If the top edge isn't uniform, hold your grinder flat and skim along the edge to straighten it up. A fillet weld is also used on a T-joint, and this is very similar to a lap weld, except you don't have that outside edge heating up quickly. On a T-joint, the top side of the weld is going to require more heat, so angle the rod into the corner to push the puddle up. If the rod is not angled enough to allow that molten pool to flow out to the top, you may leave undercut. With 60-10 or 60-11, always bring the arc back to the leading edge to fuse the corner. Angle the rod to push the puddle up. Watch the top side to avoid undercutting. The filler rod, 60-13 or better yet 70-18, will provide more weld deposit. In the flat position, hold the rod nearly perpendicular to the weld, making sure the molten pool is flowing out both on the top and the bottom. Try running straight, maintaining a uniform arc gap and travel speed. If you need a bigger weld, try using a larger diameter welding rod or stacking up weld beads. Overhead is the same as flat. Hold the rod nearly perpendicular to the weld, angled to push the puddle up. Maintain a uniform arc gap and travel speed, not letting the metal or the weld deposit overheat. For more weld, stack beads from the top down. On a vertical T-joint, downhill is easier. Use a modified circular motion, always coming back to the leading edge, then pushing the puddle out to the sides. Set the amperage high enough so the puddle spreads out and travel fast enough to stay ahead of the molten filler metal. Watch both sides to avoid undercutting along the edges. 70-18 uphill will build weld faster. For the first pass deep in the corner, angle the rod up slightly. Pay attention to the arc gap, following the base metals into the corner and along the sides. This is very subtle. It's just a little movement into the corner as you're coming across, but jamming the rod into the sides cools the weld down, and long arcing across the center creates more heat. Most of the problems with running uphill come from not maintaining a consistent amount of heat. When the arc gap varies, the heat varies, making it difficult to adjust the travel speed to keep the filler metal from spilling down. Try to maintain that arc gap. As soon as the puddle flows out to the side, move into the corner and across to the other side. Let the puddle flow out and move back. Set the amperage and adjust the travel speed so you don't have to wait too long on the sides. As you gain experience and physical control of the rod, you can try to carry more metal uphill. But while you're learning to weld, just get that first one deep in the corner, keeping it uniform and avoiding undercut. If you need more weld, maintaining the arc gap on the second pass is a lot easier. Depending on the amperage setting, slow down or hesitate on the sides until the puddle flows out. Move across the center a little quicker and slow down to let the puddle flow out on the other side. Then just side to side, keeping the upward progression tight. For heavier metal and more weld buildup, you can either stack weld beads side by side or use a weave bead. T-joints in any position will draw in the direction of the weld. If you can get to both sides, alternate welding on one side, then the other until you're finished. Last is corner joints. Depending on the weld position and what you want the finished corner to look like, there are choices in preparation and fit up to provide good penetration. One piece can be beveled at a 45-degree angle, opening it up so you can get the rod all the way to the bottom. The beveled edge is going to heat up quicker than the flat. Angle the rod into the joint, making sure the puddle flows out and ties into both pieces. A first pass of 60-10 or 60-11 will provide good penetration and is easier to handle in the bottom of the joint. With 70-18, try using a 332 diameter rod for the first pass, especially in the horizontal or vertical weld position. Keep the top of the filler beads flat to avoid trapping slag and leave the top edges as guides for the cap. On thinner metal, you can tack up the pieces without a bevel, then use a grinder to groove the joint. For ornamental type projects, you can grind the weld for a nice square corner. Corners can also be fit up butting the inside edges. For maximum penetration, tack up leaving a small gap. This type of fit up requires less metal preparation, and for ornamental type work, the weld can be polished for a more rounded corner or ground flat for a beveled corner. In the horizontal position, angle the rod into the corner, fairly perpendicular to the weld, and maintain a uniform arc gap. When both pieces are the same thickness, they should heat up evenly and relatively quick. With 70/18, adjust your travel speed so the puddle flows out to the top and bottom edges, but move fast enough to keep the weld deposit from sagging. Because both edges are heating up quickly, the filler metal will be more fluid, limiting the amount of weld buildup you can handle without having it sag. If you need to make 2 passes to fill the joint, run the first one fusing the corner and out to the bottom edge. Use the second pass to fill in the top. On thicker metal, plan the weld, leaving a little of the corners for the final series of passes. In the vertical position, downhill will make a flatter weld and will probably require more than 1 pass. For vertical up with 70/18, the outside edges are going to melt fast, so try using a smaller diameter rod for better control. Pay attention to the arc gap, following the base metals into the corner and along the sides. Keep moving. You won't have to hesitate at all on the outside edges. On any type of corner joint, you want the amount of weld to equal the thickness of the metal. If you have any concerns about the strength of the joint, you can make a fillet on the inside, but this will tend to draw the pieces in the direction of the weld. Whenever possible, always try to make the outside weld first. Well, I hope I've given you an idea of how to put 2 pieces of metal together. There are many more options in metal preparation and fit up to provide for penetration, limit the effects of the metal drawing, and reduce the amount of filler metal deposit. Regardless of the type of weld joint you're working on, you need to experiment with the amperage, rod angle, and travel speed, learning to control the amount of weld deposit and figuring out just how much metal you can carry without having it sag or drip. Make slight adjustments in the travel speed when necessary to maintain the puddle, and use the rod angle to control the shape of the weld buildup. Focus on the weld puddle, watching the sides tie in and keeping the filler metal from overheating. Above all else, take your time, have fun with this, and work safely.